Thanks, Christian, and thanks, Angus, for having me on the Angus show, I think we should call it, or something like that. Fancy name. Hopefully you can see my screen and this red cursor flying around. If you can't, then drop me a little message in the chat area. So as the guys have introduced me, my name is Malachy from Alan White Design, and we're a civil engineer consultancy based in Scotland, but we have office in London as well. I myself am a director of the Temporary Works Forum. And if you don't know what the Temporary Works Forum is, please have a look at the website. It's a lot of information there on temporary works that's very beneficial to both contractors, clients, and consultants. I'm also a member of the BSI committee for Eurocode 9, the design of aluminium structures. That's enough about me. We'll move on today to the presentation, which is bridge maintenance temporary access. So I'm going to focus on the maintenance side of things because it is slightly different beast to the construction side, but there are some similarities, and maybe we could look at that in another presentation in the future. So the format of the presentation is going to be, I'm going to briefly discuss the history of access to bridges. I'm going to look at some of the accident information that we have from the years, and look at deaths and possible improvements in the number of accidents and deaths that have happened on site. Going to look at the more modern access methods that are in use today, and then at the end I'm going to look at some of the codes that we work to, and a bit of a design example when we look at loading. So what is access engineering? Well, the actual definition is this: provision of working platform that is suspended at intervals from a structure to allow for safe place for operatives to carry out a process to the structure, such as construction, refurbishment, or maintenance. That is a bit long-winded. That's the official version, but I see it as providing a safe place for people to work from. It's as simple as that. So if you're looking at a project where you're doing repairs to the underdeck of a bridge or any type of bridge structure, then the actual challenge there is getting the operatives to the workplace in a safe manner. Yes, the main priority for the work is the concrete or steel repairs, but as a proportion of the project, that's a smaller proportion of the project in terms of design and workload. So I'm going to talk a bit about the history of access. So the original access system is the BOSUN'S chair, which comes from the shipbuilding side of things. Those of you who are familiar with it. What is the BOSUN'S chair? It's essentially a timber plank with 4 holes in the corner. You can see my cursor. A rope is put through these 4 holes and bridled at a central point. And then that is your primary means of access. So this has been used extensively over the course of the 20th century and before that in shipbuilding and in bridge access. And the majority of the maintenance work that was completed on the Fort Rail Bridge over its lifetime has been completed on a system as basic as this. So an interesting story on the Fort Rail Bridge, when they started doing the final painting system where they were applying the sophisticated epoxy type paint recently, they were replacing the lead paint, and they found that on one side of the bridge the lead paint was at least twice as thick as the other side of the bridge, and that happened to coincide with the leeward and windward faces of the structure. So the scenario they had here is that when the guys had a wet day and it was inclement weather, they'd go and paint the sheltered side of the bridge. So you have some places where you have a couple of inches of paint, and then on the opposite side, on the windward face, you've got some areas which have very little paint. So it's just an interesting fact that I got from Alan White Design when we were discussing this. Alan White, we were discussing the presentation. So while it's something that was used extensively in the past and there were lots of accidents on it, it still is something that's used in rope access nowadays, but it's not the primary device or the primary form of support. It's actually just a rest device nowadays. So I've used these in the past myself as well. So when you're in a harness for a prolonged period of time, you do get quite sore around the thigh region and the chest. So you have the BOSUN'S chair, which you can have with you when you're working, and you can slide it under your backside basically, and it pulls you up slightly and takes the pressure off the harness, and it just gives you a bit of relief when you're working in that position for extended times. The next system I'm going to look at are pick boards. So pick boards, what you have here is, you can see the underdeck of this bridge, and you've got a horizontal tension cable spanning from left to right, and this is the pick board here underneath it. So off this tension cable, they put a stirrup cable or a lasso type cable underneath it, and into that they slide a board. The board looks similar to this picture here on the right hand side. It essentially was a ladder placed on the flat with a piece of plywood put on top of it. Not something I would ever want to get on for access, but you know, some people hadn't options in the past. For those of you familiar with young man type boards, it probably is an early version of that, I would say. But the issue with this is the operatives would straddle the ladder, and they would shuffle along the ladder from left to right until they completed all the repair works overhead. And then when they completed that line of repair works, they would then come along to the end and grab this lasso stirrup arrangement here and just push it along the cable. So prone to rotation, as you can imagine on this. No edge protection. The operatives weren't separately harnessed to the bridge. So, you know, a lot of accidents and deaths. So it's not something you'd want to use in a modern scenario. The next up is a catenary scaffold. And one way of describing this, I suppose, is almost a continuous pick board. So the difference with this is you've got two horizontal tension cables, or catenary cables, parallel to each other, side by side. Then they're picked up at intervals of approximately a meter or so with vertical pickups, and they're fixed to the support structure. Then you get a timber board or planks or whatever it is, and you span this between the two cables, catenary cables, and you hook this board onto it to stop it sliding off or resisting uplift. Very flexible system. It first came about in the US Army Guide in 1926. That's where it originated, and you know, it was used commonly over the years. Very flexible system, but it did serve a purpose. Next one up, which I'm not really going to go into a lot of detail, is scaffold. You know, scaffold in its various different materials and forms has been used on bridges forever. The image on the left here is the Fort Raid Bridge being constructed, and you had a lot of scaffold and access items on that, which you know, were predominantly made from timber, I would imagine. The picture here on the right is the Clifton Suspension Bridge, and you can see a kind of a timber access scaffold here as well. Luckily, our industry's moved on a lot from that. So now you've got timber and bamboo in the Far East, but we have a lot of steel and aluminium products. You used back then, you would have drop scaffolds, which are the scaffolds that are put underneath the bridge deck during works, and they're still quite common and used today. So all these different kind of historical systems, what are the kind of accident rates? So here, unfortunately, is the death statistics that were around in 1975. So these values are based on 1 million man hours worked. So the coal mining was the most dangerous industry back in 1975, with 21 deaths per million man hours, 100 million man hours worked, followed closely by bridge maintenance. So back in that time, there was an onus in increasing safety with the Health and Safety at Work Act. And I think the industry in general, in construction and infrastructure, was trying to improve safety and decrease deaths. So we'll revisit these figures later on for our current targets, or the current death rates, and see how they compare. So now I'm going to talk a bit about modern access systems. These are systems that I have had experience with. There are lots of other systems that I haven't covered in this presentation. So forgive me if I haven't discussed your system in any detail. So the first one I'm going to start off with, and it will look slightly familiar to you, is a catenary scaffold. So while it is a historical system, it is still used today, although it's a lot safer system with more redundancy in it, and it's made from either aluminium or steel components. So what you have is you've got a lightweight system here. It gives good coverage underneath the bridge structures. You can see here in the top left-hand corner. You can basically deck out the entire underside of the bridge. On the top right-hand corner here, then you can see we've got catenary cables, or horizontal cables, that are running along the full line of the bridge here. I think this is actually a jetty, a harbour, and another cable along here. And it's picked up at intervals of about 1.5 meters to 2 meters here. with these drop cables that are fixed into the soffit of the bridge. So it is a lightweight system, but there again, it is flexible to impose loads, winds, and impose loads on the deck. Is definitely one of the cheaper systems to install and have over the lifetime of the project. It does need a lot of drop points, as you can see here. It can be difficult to achieve redundancy, and redundancy I'll discuss a bit later in the presentation. It's very hard to adapt this once it's been installed. That is one of the challenges with this system. You need to get it right day one. And a lot of time with bridge access and platforms, people realize at a later date when they're on it, they need to get to another point. So adaptability is a challenge, but we're talking about spans of less than 2 meters here. You can see this lower one here where we didn't have any points underneath the bridge soffit. It's actually the Queensferry crossing to fix in. We couldn't just go drilling the brand new bridge. So it had to be bridled with the supports taking off at an angle here and taking off in a Y-type bridle scenario up to the outside of the structure. Next one we're going to talk about is by far and away probably the most popular method of accessing underside of decks, and it's a suspended scaffold. So if we take this bridge cross section here, you can see the bridge trusses into the page here on the left and on the right. And then you've got the underdeck bracing structure throughout the underside of the deck, and you've got the wings here. We've also got some bracing in that as well. So it's a very, very congested environment already from the permanent structure. And what you have here is, if you're trying to lift a platform in there, it probably is achievable to put a platform in there, but it can be quite difficult to get around all these lower members. So a suspended scaffold is definitely an option when you're trying to do this. You can see the scaffold here underneath the bridge structure, which is actually the Fort Road Bridge. And then this is the actual layout of the structure of the scaffold. Very labor intensive, this kind of work. You do need a highly skilled scaffolding workforce. There's a lot of self-weight involved in it. It can be quite large, which depending on the bridge, if it's already in trouble or its capacity is reduced, you may need to look at lane closures or potentially bridge closures. But on all the projects we've worked on with these, it's usually not been a problem. There are a significant number of vertical supports and bracing, and the spans are quite low because you're just spanning a scaffold tube between supports, so maybe 1.5 meters or so, maybe up to 2 meters, depending on your loading requirements. So here we have some images of the suspended scaffold. So these weren't used for painting works, which I'll come back to in a minute. They were used to remove these walkways and repair them along the underside of the deck. It is quite congested in here with these vertical drops and also these braces. But what you do get is a nice, clean, open working platform, as you can see from these images. It is quite safe. And the beauty, when you know you've done a good access platform system, is when the operatives don't actually realize they're on a platform. That's probably the best way of doing it. And you wouldn't really notice that you're on a platform here until you look out over the edge and you see a 100-foot drop into the Fort Estuary. But that's the beauty of it. I did talk about connections here, and this connection detail here is what it's standard gravlock type connection, beam clamps, whatever you want to call it, onto the bottom flange of a girder. And a lot of projects that you would do, you'd clamp, the clamp detail wouldn't work that well because you may be painting this structure and you need to get paint onto this connection point underneath the gravlocks. So you'd have to come up with a regime where you could actually take off these connection points and somehow paint underneath, above them and around them, and then put the connections back on again. So that's a challenge in that. Next one we're going to talk about in a bit of detail, and it's one of our pet items at Allen White Design, are space frames. So space frames are essentially a three-dimensional truss. They're fantastic structural elements to work with. They're very strong, they're lightweight in themselves, but also the individual components are lightweight. They can do quite large spans of 25 meters plus, very modular, so they can be built by non-skilled workforce, and they're very rigid, so when you get wind loads and imposed loads applied to them, you don't really feel that as an operative on the platform. So you typically have a structure that looks like this, size of a tennis court, typically that kind of scale. You put 4 cables on it, 1 in each corner, and you lift it tight to the underside of the bridge to do your works. You can change the depth of some space frames. So what you have here is strength weight ratio, but also you have a balance on how far you want to span and what load you're going to put in to the bridge. A lot of these bridges have been reduced in strength, so there's a reduction on the reaction loads that you can put in as support points. You have to do a bit of a balance between, yes, I can get it stronger and span 20 meters, but can the bridge take that reaction point? So there's a bit of a balancing act when you're looking at these long span suspension platforms. So I'm going to talk about 2 different versions of space frames. In this slide, I'm going to talk about how it fails, which sounds a bit weird, but we know exactly how it would fail, which means we know we can make it as strong as it needs to be, a space frame. And as space frames are definitely the strongest structural component you can use for access. So this is a pin space frame. You've got a node here, which you see in red, which is all the same component, and then you've got horizontals that fix into it to form the upper section, and then diagonals throughout. So in this space frame, you've basically got 1, 2, 3 components in total, which is great for transport and assembly and repeatability. And then the boards just sit on the top of that. But the scenario you have here is in this truss, all the members are in axial load only, apart from the top cord, which is in combined compression and bending, because you've got it supporting the boards and the load. So what happens here is when you do get a failure load in that, you've got your bending moment diagram here, it'll fail in combined compression and bending, and that's quite a sudden failure. So there's really no warning or early warning on that. So while it's a great system, there are, and I'm not knocking that system and at all, it's a node and stick type scenario. You can have scenarios where you would get more warning from different types of space frames. So the next one we're going to look at, is a ductile space frame. So this is the same scenario here, but the slight difference is that on the top here, we've got 2 cords, and one of the cords is continuous all the way through. So if you're familiar with kind of RC slab design and intermediate supports, what you have is a scenario here on the top cord where you get hogging over the intermediate supports, and that lifts your entire bending moment diagram, which reduces the load, the combined load in this member, and then suddenly that means that the failure member is the bottom cord, and the bottom cord fails in tension. Because you've lifted that bending moment diagram on the upper side, it means that the weakest member now is the bottom, and what you have in a tension failure, it's not a sudden failure. You get kind of notice of it. Speaking to Alan White, he's always said that it almost screams, the member screams when it's getting elongated and pulled apart. We're talking about failure methods here, but you need to know these failure methods in detail so you can look at redundancy, and that's something we're going to discuss in detail in a while. Next system is a scaffold beam grillage. These are very common. They're very versatile. They're all off-the-shelf components in the scaffold industry, so procurement time is reduced on these. And essentially what you have is you've got a beam that spans between 2 points. The beam in this is an X-beam, just because that's what we use quite a bit. Other beams are available, and it can be done in any kind of system you wish. But you've basically got scaffold beams spanning parallel to each other, typically at 1 to 2 meter centers. And then you've got another frame, or you can do it in scaff tube, bracing these platform main primary members together, because they have to be restrained at 1 meter centers. And then you put a plywood covering over the entire structure. So the beauty of this is a lot of this can be prefabricated and brought to site ready to lift to the underside of the bridge. You could also prefabricate it on site at ground level and then just transport locally across the site to lift up into position. They are very versatile. You can create lots of different shapes and to suit bridge piers and decks and that. And I'll just go through some of those in a moment. The only probably issue with this is, I suppose, is it is comparatively heavy. But we haven't come across a project where we've not been able to deal with the reactions through the platform in some way to satisfy the check-in engineer for the bridge. So these are some images of the scaffold beam grillage. So in the top left-hand corner here, you've got a grillage platform similar to what I described above. But in addition to that, you've got a tower, a gantry tower for loading. So what happens here is a truck can pull up along here, and this is actually the cycle lane on the Erskine Bridge, for those of you that are familiar with it. So the truck with the materials for the work can drive up here, and if you're doing bridge repairs, you need to got a lot of because they're doing the repairs, they're either doing blasting or grit blasting or hydro demolition, and you can't just let that material drop into the water course like you would have in the past. So that material needs to be collected on the platform and then taken off, and you can have quite a lot of material builds up and you need to get it off. And what we have is we've got a gantry crane here. So the gantry crane, when the truck pulls up, the gantry crane is on a runway beam here at the top. The crane can come in tight to the tower, lift up the materials, roll out over the top of the flatbed truck and drop it down onto it. And the same, but in reverse, for bringing materials on like paint and epoxies and grout. So that's a neat way of doing it here. The top right hand corner, I don't really need to explain this location. It's the Fort Road Bridge with the rail bridge in the background. But this is a nice picture because it gives you an idea of, we're talking tennis court size shape again here. Put 4 cables, one in each corner, and you pull it to the soffit of the bridge. You can see here the handrail systems that are all built into it as well. So it's a neat, safe platform. Bottom left-hand corner here, I think, is the Fort Road Bridge again. The reason I put up this image here is you can see a scaffold gate in this end of it here, which is a bit unusual to see it randomly with nothing on the other side of it. But this platform is left stationary in its position, and the permanent gantry that ran on these tracks for the bridge maintenance was used to travel up and down, and they could walk between them for getting operatives to the work face. This bottom right hand corner is a tiered platform. So this top right is what a basic grillage platform looks like. This bottom right is probably the most complex one we've ever done. So you've got quite a large span bridge. We're looking to get to the underside of the soffit to do painting works. And it's tiered. You've got a level of scaffold here, another level of scaffold here, and then there's an access stairway over the top as well. So that's a bit about scaffold grillages and modern systems. And really, what has that done for our accident stats over the years? Well, if you look at the top here, coal mining, the accidents have disappeared, but that's more or less because the industry has disappeared. But bridge maintenance has taken accidents down from 18.5 people per 100 million man hours down to 3.5. And that equates to an 84% decrease in deaths within the industry. So that's a fantastic achievement. We can still go further with that and try and get rid of these altogether. And it's through contractors and clients investing in these modern access systems is where we can improve safety. Going to talk about platform design codes. So there are a number of codes that you go to for platform design. BS 5974 is the code that you go to, but it doesn't really give any information on loading requirements of platforms. So you've got an option then of going to BS 5973 or 1808. I would always choose 1808. BS 5973 is for access scaffolds, but it'll give you a blanket UDL of light duty, heavy duty, medium duty. And 1808 gives you a different scenario where you've got patch loads. And I'm just going to go through patch loading now for those of you who aren't familiar with it. So patch loading is where you take a concentrated load and apply it in the most onerous locations on the platform to get a design to work. So if the platform is rated for 500 kgs, and this is a platform here with 4 supports, these stars are the 4 supports in the 4 corners. So we'd apply that rated load at an intensity of 2 kilonewtons per meter squared. So you take whatever your safe working load it is and divide it by 2 kilonewtons per meter squared, and that dictates the area you need to put the patch over. And you apply that at midspan. You apply it between the 2 edges, the edge between 2 supports, and you'd apply it at support. So you're basically getting your worst case moment at midspan, the worst case moment between supports, and the worst case reaction at a cable. And why do we do this? Well, I'll compare the reactions between a patch load version and a blanket UDL version. Well, I've kind of done these the wrong way around, but if we've got a 10 meter by 10 meter platform that's got 1 kilonewton per meter squared on it, so that's 100 kilonewtons applied to that platform. So you're looking at a live load reaction of 2.5 tons per support, 2,500 kgs, which is crazy, because you could be sending 2 men with paint and materials up there, and you're putting 10 ton on the platform. So what we tend to do is go down the patch load route, where you apply 500 kgs locally over the support, and you're getting a live load reaction here of 500 kgs rather than 2,500 kgs. And I've seen scenarios in bridges where people have insisted, clients, contractors, consultants have insisted and used the blanket UDL version, and they've actually had to reinforce the bridge to take the load, which was a phantom load. It didn't exist, and you're just costing yourself money and time. So we would probably default to 1808 for the majority of our projects. Avonmouth Bridge disaster in 1999 was a project where 4 operatives unfortunately lost their lives. So a platform was blown off the runway beams, and 4 guys dropped to their death. What happened was that safety devices on the platform were ignored, because it allowed the people to get the project done quicker, and they were on bonuses based on that, which is a tragedy. So what happened was that the end of this platform here, you can see, typically would have been held by 4 cables, 1 in each corner, and the safety mechanisms were removed. So the platform was in a gust of wind, and it rolled off the edge of the bridge beams that were supporting it on the trolleys, and it dropped on one side here. All the operatives fell to their death, and then with this big sail of wind area now, the platform was in the middle of the span, and it blew all the way to the pier, and it smashed into the scaffolding at the pier as well. A tragedy that should never have happened, and since then, 1999, the HSE have brought in stricter legislation on platform design. I'll just go through that quickly because I know I'm running over. They've kind of brought around the factors of safety, whether they're 2, 5, 6, 8, 10, that is not sufficient anymore. You have to have structural duplication throughout the access platform. So if anyone is familiar with permanent works designs and progressive collapse, then you'll be familiar with this. You take a platform that's got 6 supports, and you load it, you figure out which support has got the highest reaction on it, and in your analysis you remove that support. And does the platform still stay stable across this line? Do you get any uplift at the back of it? You have to make sure that this is an accidental case. You have to make sure that the operatives can safely get off that platform if there is a failure on any of the support system. I could go through that in a lot more detail, but I'm just going to move on to the summary. So summary, basically, we've got a lot of safety improvements over the years that have saved lives. The design approach, I think, is critical when you're looking at a blanket UDL or patch loads. The system choice, it's a bit of a challenge. Strength, weight, price, procurement, existing bridge condition all play a part of this, and you should always have redundancy throughout. That's key to any design of access under bridges. If something fails, there's a backup system to deal with it. Just a little plug, I'm working on a separate project myself at the minute called Bite-Sized Temporary Works. So in this, I'm creating learning videos, which are free learning videos and CPD opportunities for anyone that's interested in temporary works, and they're currently being produced, and in the next week or so they'll be available on our LinkedIn page and our YouTube page. So please have a search for Bite-Sized Temporary Works. Thank you to Angus for having me on the Angus show, as we'll call it, and any questions, I'd be delighted to take them.